So we've talked a lot about limits and slopes and tangents and secants, and it all kind of might seem unconnected and a bit nebulous right now. Let's try to connect it a little bit to the core of calculus here, and that's to talk about defining what we call the derivative using limits. It just so happens that the way that we've defined this word derivative is that it's just the same as the instantaneous rate of change. So what we talked about for instantaneous rate of change, which is the same as the slope of the tangent line, it's also what we call the limit definition of the derivative. In other words, the derivative of f with respect to x, or sometimes we'll write this as f prime of x, is the limit as h approaches 0 of f of x plus h minus f of x over h. So exactly what we've just been doing work on in the last video, just with a new fancy name. Right? As I just said, we read this as f prime of x. So this is our limit definition of the derivative. Sometimes you'll hear this, particularly in the book, as derivative from first principles. And I think that's just a fancy way of saying don't use any of the tricks that you're going to learn later on. Go back to the way you first learned it, demonstrate your knowledge of limits, and calculate the derivative. We have two ways to notate the derivative with respect to x. That's just what this abbreviation here means, WRT, with respect to. One of them is what I just showed you, f prime of x. So again, f prime of x. And the other one is this d by dx, or sometimes you'll see dy by dx. So we'll say d by dx, or dy by dx. Sometimes I'll just say the derivative with respect to x, or the derivative of y with respect to x. So derivative with respect to x, or the derivative of y with respect to x. So just two notations. We use them pretty interchangeably in calculus. For me, it just depends on the type of thing we're working on. You'll see what I mean as we go through the chapter. So let's practice a little bit with our limit definition. If f of x is the square root of x, find f prime of x when x equals 9. In other words, find f prime of 9, right? You can see it notated that way as well. And again, we're going to find this derivative from first principles, which means we're going to use the limit definition of the derivative. So let's just start by finding f prime of x. That's probably a good way to start, good way to go. So f prime of x equals the limit. As h approaches 0, we're going to start by copying the thing down in general. It's just good practice. It helps it stick in our head, and it helps us avoid missing steps. Well, now let's evaluate. F of x plus h is just the square root of x plus h. F of x is the square root of x, and that's all over h. Let's see if I can create a little more space here. Now, you're looking at this, I'm looking at this, going, what do I do from here? Because it doesn't really look like there's any good way to simplify this, right? I can't really combine anything on the numerator. I need to do something because I'd be dividing by 0 if I plugged in h right about now. Well, we've heard of rationalizing the denominator, right? When we've talked about rationalizing in the past, we've talked about rationalizing the denominator. Multiply by the denominator, and it all kind of makes things a little bit easier to work with. Well, we can do this to the numerator too, with the numerator. This is something that you weren't necessarily taught maybe in Algebra 2, because we don't really talk about doing this with the numerator in Algebra 2. It's just not relevant at the time. But it is something that we can do. So one thing you might remember from rationalizing is if you have two terms here, we don't just multiply by that term, we multiply by what we call the conjugate. So instead of having the subtraction in the middle, we're just going to put addition in the middle. Whoops. And whatever I do to one side, I need to do to the other. So this is my rationalizing step, right? Rationalize the numerator. And what this is going to do is allow us to simplify this better. So the whole reason we rationalize, and by using that conjugate step, is that it creates a difference of squares in the numerator, or wherever we've rationalized. So I'm just going to make a note here. This is a difference of squares. So save yourself the time. This is just square the first term, square the second term, and subtract. And then this whole mess just kind of stays the way it is. And I'm not going to do anything with this. I'm just going to leave it the way it is. So simplifying further, x plus h minus x is just going to give me h over this entire monstrosity in the denominator. But it's getting nicer because my h's can cancel out. It leaves me with an almost fully simplified, actually pretty much fully simplified, expression that I can evaluate for h equal to 0. And it leaves me just with 1 over, well, let's see here. I have the square root of x plus the square root of x. So that's 2 square roots of x. This is my limit, sorry, this is my derivative in general, right? So if f of x, what we figured out so far, if f of x is the square root of x, the derivative of f is 1 over 2 square root of x. Well, we're not done solving this problem because I want to know what f prime of 9 is, right? Find f prime of x when x equals 9. So f prime of 9 is going to be 1 over 2 times the square root of 9. Well, the square root of 9 is 3. 2 times 3 is 6. So the derivative, the slope of the graph, if I were to graph this, at x equal to 9 is 1/6. And this kind of makes sense, right? Because if I graph this function, square root of x, my slope slows down. My slope kind of tapers off, right? You can see that it's not growing as quickly when you're all the way out here as you are when you're down here. So it does make sense for the slope to be less than 1. This is just kind of a way to start trying to connect the ideas behind slope and derivatives. So one last point in this video, if f prime exists, we say that f is differentiable at x, which is just a big word for saying that we are allowed to take the derivative and we can get a result. A function f is differentiable everywhere if f prime exists for all x in the domain of f. So differentiability, we'll start to connect this a little bit to some other problems in the next section.